Okay, welcome everyone to my talk. I'm Konstantinos Mamouras, and I will present joint work with Agnishom Chattopadhyay. So as you probably all know, classical regular expressions, or regexes, are built using concatenation, non-deterministic choice, and Kleene star. Due to their simplicity and their immediate correspondence to finite state automata, they have very nice computational properties. But real-world regular expressions, on the other hand, use more constructs than just the regular ones, such as bounded repetition, Lookaround assertions, and back references. In this work, we specifically focus on the challenges brought by Lookaround assertions, which are further subdivided into positive look ahead, negative look ahead, positive look behind, and negative look behind. So why do we care? Well, regexes with lookaround are widely used for extracting information from unstructured data. They have found many applications in domains such as network intrusion detection and malware detection. The key computational problem here is called regex matching, which is about finding occurrences of patterns in datasets. Unfortunately, existing regex engines that support lookaround rely on backtracking search, which is a very inefficient algorithm that has exponential running time. In this work, we show that we can actually do much better than this. So let's start with an example that shows how lookaround is used. Suppose that we want to extract the area code from a US phone number. This is the pattern that we would use for this extraction task. Let's go over it bit by bit. This is a character class that matches a single digit. This is a pattern that matches 3 consecutive digits. This suffix pattern describes strings that start with a dash, followed by 3 digits, followed by a dash, and then followed by 4 digits. So the positive look ahead for this pattern is different in that it does not capture the suffix substring. So what are the main observations here? First of all, the entire string must have the form of a phone number, but only the first 3 digits of the string are extracted or captured, as we say. The substring, on the other hand, is not, the substring that corresponds to the suffix pattern is not captured. This means that in this example, the lookahead specifies the context within which the area code should occur. Let's look now at another example for specifying password requirements. This is the pattern that we will use. The character class dot matches a single character. So this sub-expression matches at least 8 consecutive characters. This sub-expression matches a string that contains at least 1 lowercase letter. This matches a string that contains at least 1 uppercase letter. And this matches a string that contains at least 1 numerical digit. Notice that the lookahead assertions do not capture the string and they overlap. This means that the entire string must satisfy all 4 password requirements. So in this example, lookaround encodes a form of intersection or conjunction. As you probably know, classical regular expressions have a very simple semantics where each expression is interpreted as a set of strings. Regexes with lookaround, on the other hand, require a more complex semantics because they additionally describe the context within which a match should occur. Before I show you the definition of the semantics, let's go over some terms. A position in a string W is a number in the range 0, 1 up to n, where n is the length of the string. We should think that positions mark the boundaries between characters. In particular, position 0 corresponds to the left endpoint of the string, and position n is the right endpoint. Now, a location in a string is a pair I, j, where I and j are positions and I is at most j. Remember from this slide that positions are points, but locations are intervals. Now we are ready to present a logical semantics for lookaround using a satisfaction relation. This is a ternary relation that relates a string, a location within the string, and a pattern. We read this as follows. The pattern R has a match in W at location I, j. And this is an illustration of a match within the string. The satisfaction relation is defined by induction on the structure of R. And I will not be showing you the full definition, but let's go over the cases of lookaround. So for the positive lookahead of the pattern R, we say that it has a match at location I, j, if and only if I is equal to j, and the pattern R has a match at location I, n. The case of negative lookahead is similar. Now, for positive lookbehind and negative lookbehind, the definition is completely symmetric. There is one important observation that we have to make here. Lookaround assertions should be thought of as being interpreted at positions. This is because an assertion only holds at locations of 0 length. Now that we have seen the formal semantics, let's go over one more example. Let's consider the pattern BC, but only if it occurs within the appropriate context where it is preceded by some occurrence of A and is followed by some occurrence of D. We can see in the string that there are 3 occurrences of BC. Now notice that the pattern .*A.* has a match at location 0, 6, which means that the lookbehind holds at position 6. Similarly, the pattern .*D.* has a match at location 8, 15, which means that the lookahead holds at position 8. From all these, we deduce that the top-level pattern has a match at location 6, 8. And in fact, this is the only match in this string. There are 2 common approaches for regex matching. One is backtracking search, and the other one is automata-based simulation. The advantages of backtracking are that it is easy to implement, and also it allows for the easy integration of advanced features such as lookaround assertions and back references. The main disadvantage is that it has worst-case complexity that is exponential in the length of the input text. This can get pretty bad, and it even has a name. It's called catastrophic backtracking. In the case of automata-based approaches, typically NFAs or DFAs are used. There is a memory throughput trade-off that can be explored here. Generally speaking, NFA-based approaches are much more memory efficient, but DFA execution can be much faster. Notice that some popular regex engines, such as Google's RE2, use a hybrid approach that combines NFA simulation and DFA simulation. Unfortunately, none of the existing automata-based regex engines supports lookaround. So if we want to use lookaround, then we're currently stuck with catastrophic backtracking. There is a fundamental obstacle when using automata for lookaround. It is known that there exists a family of regexes with lookaround such that the smallest DFAs recognizing them have doubly exponential size. An implication of this fact is that any deterministic streaming algorithm for matching regexes with lookaround requires exponential memory. For this reason, we propose an algorithm that is not streaming in the general case. Our algorithm may perform several passes over the input text. In particular, it performs left-to-right passes for evaluating look-behind assertions, Correspondingly, it performs right-to-left passes for evaluating lookahead assertions. Each pass performed by the algorithm should be understood as the execution of some non-deterministic automaton. I will explain now the algorithm using the example that we saw before. So the pattern we're looking for is BC in the context that I described, and at a high level, we perform the evaluation in a bottom-up manner. First, we start with a look-behind assertion, and we evaluate it with a left-to-right pass. So notice here that we're searching for an occurrence of A. So in the beginning, the output is 0 until position 4, and it becomes 1 from that point on. Next, we evaluate the look-ahead assertion with a right-to-left pass. Similarly, we're searching for the occurrence of a D. So the output is 0 until position 11, and it becomes 1 from that point on. Now, we abstract the top-level pattern by replacing the look-behind with Q0 and the look-ahead with Q1. These expressions, Q0 and Q1, should be understood as some kinds of queries to oracles that can immediately resolve the truth values of the assertions. For this reason, we call this highlighted expression an oracle regex, and then we proceed to evaluate it with a left-to-right pass. So let's see how this proceeds. So we're looking for a BC occurrence. So going from left to right, we find the first occurrence at position 4, but we don't have a match here because the look-behind does not hold at position 2. We continue until position 8, where there is a match because both the look-behind assertion holds at position 6 and the look-ahead assertion holds at position 8. And then we continue until we find the other BC at position 15, where there is no match because the look-ahead does not hold at position 15. The algorithm that I just described stores the output from the first 2 passes in data structures that we call oracle tapes. Then the next pass of the algorithm is performed using an automaton that I call an oracle-NFA. You should understand this as being an extension of epsilon-NFAs, where the automaton has access to both the input string and the oracle tapes. An additional feature of this automaton is that it can perform queries to the oracle tapes using special epsilon-transitions that are annotated with oracle queries. And you can see 2 such transitions in the diagram on the slide. Another important observation is that the memory footprint of this algorithm is determined by the space that we need to store the oracle tapes. So the footprint is big O of Kn, where K is the number of Lookaround assertions that occur in the pattern. The main theorem is that the regex matching algorithm that I showed by example in the previous slides has time complexity big O of Mn and space complexity big O of Kn, where M is the size of the pattern, N is the length of the input text, and K is the number of Lookaround assertions in the pattern. We have also implemented several performance optimizations on top of this base algorithm. I will only discuss one of them, which is about reducing the memory footprint of the algorithm. I need a definition first. We say that a regex is unidirectional if either all lookarounds are look-behinds or they are all look-aheads. Now, if a regex is unidirectional, then the algorithm can simply perform a single pass over the input, and therefore we do not need to store oracle tapes. An implication of this is that the memory footprint can be reduced from theta of Kn to theta of K. In particular, if all lookaround assertions are look-behinds, then the algorithm performs a single left-to-right pass over the input and can be therefore be regarded as a streaming algorithm. We have implemented our algorithms and the optimizations, and we have evaluated them experimentally using the Snort and Suricata datasets. We have compared our algorithms against PCRE and Java's regex library, both of which are state-of-the-art regex engines that are based on backtracking. The main observations from our evaluation are the following. First of all, both our algorithms have linear running time in the length of the input text, and the optimized version is at least 10 times faster than the base version. Moreover, the running time of PCRE and Java is superlinear in the length of the input text. In particular, our optimized algorithm is 250 times faster than PCRE for text length 1000, and it is at least 4,000 times faster than PCRE for text length 10,000. Now, I'd like to conclude with a summary of our main contributions. We have presented a formal semantics for regexes with lookaround using a satisfaction relation that relates a string, a location, and a pattern. We have proposed an efficient algorithm for matching regexes with lookaround that has complexity big O of mn. And we have shown that unidirectional regexes can be matched with a single pass over the input. We have implemented our algorithm and several performance optimizations, and our evaluation shows that our implementation has much better performance than PCRE and Java's regex library over the workloads that we considered. This is all. Thank you for your attention.
Questions? Hi, could I ask about back references? Have you thought about those much, especially when you have the back references inside the lookarounds or the capture groups?
So that's a great question about back references. So they present a unique challenge because they take us beyond regularity, whereas everything that we consider so far is in some sense regular. I would say probably the starting point there should be to look at special cases of back references that are indeed regular, when, for example, you're capturing something that is bounded in length. And I would say maybe the next step should be the use of back references where the regular expression has some kind of determinism property. So beyond that, I am not sure how it would work out if one wanted to have an efficient implementation of back references. I think that's a challenging question.
Thanks for the talk. The example you gave had a certain number of lookarounds that were then compiled into a final oracle-NFA. But if you have nested lookarounds, do you then you have a dependency between the oracles? Does this then induce multiple paths that would be multiple passes over the string that's then reflected in the efficiency?
That's a great question. Indeed, if there is nesting, then the algorithm would proceed in the same way. You would just have to do more passes. The key thing to notice here is that if you perform the passes in order of dependence, then you already have the oracle tapes that you need in order to perform the next computations.
So in that case, would the complexity be parameterized additionally by like the depth of nesting?
No, the bound that I showed would still be the same. Right. So there would be the upper bound would be m times n, and in order to prove that, you have to see that the oracle regexes that are used, the sum of their sizes is equal to m. So this is really the key observation there. So as you proceed in a bottom-up manner, you keep breaking down the regular expression, but the oracle regexes that you consider, their sizes will always sum up to m.
Okay, thanks.
Mm-hmm.
So I had 3 questions, but one of them was just the last one. So let me ask 2 questions. What happens if you have a star and have a lookaround in it? Don't you need to scan multiple times, like the case with a nested lookaround?
That's a good question. No, you don't need to scan several times, because when you do a single pass, you resolve the output for all positions. So you store that in the Oracle tape, and then you have the answer for every position in the string. So you're free to use those outputs from that point on. So then in the start implementation, there will be a loop in the Oracle NFA, but that will consult the same tape every time.
Sorry, I didn't ask the right question. I think I understand that they can do the Oracle. What about the string one that you briefly went over?
So for the streaming case, I said that you need to restrict yourself to regular expressions that only have look behind. So you can perform a left to right pass. But then if you look at the regular expression, there can be dependencies between the look behinds. So if there is nesting, there is going to be dependence. But then you're going to perform the computation for each one of them in topological order at every step, so that every time you need something, you have already computed it. So you do a left to right pass, but within a single step, you process the look behinds in the topological order of their dependencies. And this ensures that the bound holds.
Thanks again, and also for the answers.